Hello and welcome to this video on rotational motion. Specifically today we're talking about conservation of momentum in a rotational reference frame. We've already talked about conservation of momentum with linear terms. We could talk about how the initial momentum will equal the final momentum in any collision where there are no outside forces acting on it or where the forces act for a very short amount of time. We know how fast things are moving before the collision and the masses of the objects we can predict how they move after or do calculations, or vice versa. This is straightforward things we've already done. In angular momentum, the same is still true. The initial angular momentum will equal our final angular momentum. But in this case, there are some slight issues here. Because of how collisions work in angular momentum, there are typically two general scenarios. You have either two objects sticking together, like a disk and a disk sticking together, or you have an object getting hit and calculating afterwards. These are the two general scenarios, and while they are very similar to linear momentum, they are different enough that we should address each one separately. We'll start with the easier one. Two objects are going to collide and stick together. In this case, I have a hoop of mass 1 kilogram and radius 0.5 meters, and a disk mass 2.5 kilograms, radius of 0.7 meters. And they stick together in a perfectly inelastic collision. This is what we've done previously. L initial equals L final. The main difference here is that because we're talking about moments of inertia, we have to talk about how that adds. So in this case, the disk is moving originally. So the I of the disk times the angular velocity of the disk will equal the two objects stuck together. Well, how do we find the moment of inertia of the two objects stuck together? Our chart has a hoop and it has a disk, but it doesn't have both stuck together. How do we do it? Well, the simple answer is we just take the two objects and add their moments of inertia to get our total moment of inertia. When two objects stick together, in this case, their moment of inertia is equal to the sum of their individual moments of inertia. So in this case, I of the disk times omega of the disk, your initial angular momentum, because the hoop isn't initially rotating, will equal the sum of their moment of inertias times the total angular velocity of the two objects after. This is straightforward. I of a disk is mr squared over 2 times the omega of the disk, which is up here, equals hoop, which is mr squared, plus disk, which is mr squared over 2, equals omega final. And from here we can rearrange and solve. Just note that these masses are different. This is of the disk, this is of the hoop, this is the hoop, this is of the disk, this is of the disk. So you can't just cancel out variables and solve, you actually have to rearrange. So mr squared of the disk times omega d over 2 divide by this entire term. 2 can move down to the bottom, and then I just need to plug in some numbers. So in this case, omega final, or omega t, the total system, is equal to 4.25 rads per second. Again, the process here isn't too different from what we've done previously with momentum problems. The major thought process, the major change in this case, is having to use the moment of inertias instead of the mass, but you still add the masses. Had the hoop hit the disk and then started moving while the disk stayed still, we'd have a different problem altogether, and we'd only use the hoop's moment of inertia, but I wanted to look at the most complicated case for you. The second style of problem that we typically see is something comes in and sticks. A 0.95 kilogram rod is 0.65 meters long and set to pivot about one end, or the black section at the top. It is initially at rest when a 0.03 kilogram piece of putty is fired at it. If the putty is traveling at 4.5 meters per second, it strikes at a point 0.60 meters from the axis of rotation. So it's hitting here as opposed to right at the tip. How fast is the putty and the rod going after the collision? We're going to treat this as a conservation of angular momentum, so the setup isn't too different. L initial equals L final. And the moment of inertia of the two together will be fairly easy. So mr squared for a piece of putty, for a point mass is what we'll treat the putty as, put a little p here and p here, plus I of a rod times omega. The problem is the initial angular momentum of the piece of putty. The piece of putty isn't moving in a circle. So how do we find its angular momentum? Well, to talk about that, let's imagine the putty moving along. If this is my axis of rotation up here, at this initial point, the putty has momentum in this direction. It's going to continue having momentum in this direction at all times. We go back to the vector definition that L is R cross P, or in other words, equals R times P times sine theta, where theta is the angle between them. And since we're talking about a point mass in most of these cases, P is just m times v. So as it moves, the angle it makes changes. It sweeps out a certain amount of area in this time, and a certain amount of the area in this time. Those angles that we have here, theta 1, theta 2, means that it's moving through angles with reference to the axis of rotation with time. Now, typically, we can calculate this, we can find it, we can find all the values, but the important bit is when it hits. In this case, it's hitting directly perpendicular. If it was hitting at an angle, we'd have to go back to the sine here. But since it's heading perpendicularly, sine of theta is 90, which simplifies down to the RMV I told you in the previous video. I wasn't lying. If it happened to have hit at an angle, like say so, I could find the angle between the two of them here and plug in my theta. As long as it's hitting at the moment of impact, for r times mv, sine theta, where sine is the angle between them, will give us the angular momentum of just that point. Now that we know that, however, we can go ahead and plug this in. We know how fast it's going, we know its mass, and we know how far out it's going to hit. These factors combined will tell me what the initial angular momentum is, which will let me solve for the angular velocity after. Go ahead and give this one a try on your own. Check back after you're done. I've gone ahead and derived the equation here. When we go through the math, we see it's 0.56 rads per second, which makes sense. The putty is very low in mass comparison to the rod. So the fact that we have a much lower velocity comparatively makes sense. Some interesting things that we can see out of the derived equation, however, if the rod had been longer and had a larger mass, the denominator would be larger, which would give us a smaller angular momentum. The final thing we actually have to talk about, though, is an oddity that we don't deal with in linear momentum: figure skating. In both cases here, the person spinning has a constant angular momentum. They have the same angular momentum here as they do here. But unlike with linear momentum, in angular momentum, you don't have mass, you have the moment of inertia term, which is a sum of all the masses based on the distance they are from the axis of rotation. So by having the arms out when you start spinning originally, you have a very large moment of inertia. But you can bring those arms in, decreasing the distance the mass is from the axis of rotation, decreasing the radius, decreasing that moment of inertia. And because the angular momentum is constant, as your moment of inertia goes down, your angular velocity has to go up to compensate. This idea, this tucking, is fundamental to figure skating, to diving, to any rolling motion. It's why when you are on anything that spins, you're told to tuck in to go faster. If you've ever been on a swing and spun around, this also happens there. It is also, very hilariously, how squirrel deterrent bird feeders work. As the squirrel tries to bring its body in closer, increase the inertia, which causes it to start spinning faster, making it harder to grip. Anyways, thanks for watching. Have a good one.